Namaste and welcome to this lecture on mathematical foundations for machine learning. In the last week we looked at the ideas of orthogonality, orthogonal projection, and then we looked at real symmetric matrices and stuff, and we had a very interesting topic there where we said, look, what is the vector, let us say suppose I have a vector x and I have a subspace. I want to find out what is that vector which best approximates the vector x in that subspace W, right. We had that we discussed that, we said that look, the orthogonal projection of this vector onto the subspace W is going to be the best approximate of the vector x in the subspace W. Now where do we go forward from here, and that is a very interesting question. The reason is we often find in machine learning where we try to fit a curve, when we have huge data we may not be able to fit a unique curve that passes through all the points. Therefore what we do is we look for that curve which is going to minimize the error between the data that you have collected and the points that fall on this curve, that means the estimates that you have in squared sense. What does it actually mean? Suppose I have this system of equations, let us say Ax is equal to b, right. Suppose I have this system of equations Ax is equal to b. Now what happens is I want to figure out, let us say I will put this A is m by n, and let us say x is an n by 1 an n component vector, and we have this b vector which is another say m by 1. So basically we say that x is an n component vector, it is an element of Rn, then b is an element of Rm, right. We have this. Now what are we trying to do? Typically we would have seen when we try to solve systems of equation, we would have looked at this as Ax is equal to b. And what do we mean by this? We want to solve for x, when A and B are known, A and B are known, right. Now what is interesting here is we will just look at a simple example and see what happens. Suppose I give you this, where I am going to look at let us say this example 2x1 plus x2 is equal to 3 and 2x1 plus x2 is equal to 4, and I tell you solve for x1 and x2. I tell you solve for x1 and x2. Now if we actually look at this system of equations where A is going to be this matrix 2 1 2 1 and x is basically the vector x is basically the unknown, basically the 2 component vector which has parameters x1 and x2, and b is basically the vector which is 3 4, right. We have this. Now what do we find here? We find that whatever value of x1 and x2 that you substitute here, we are not going to get that right hand side 3 and that right hand side 4 simultaneously. That means we are looking for the values of x1 and x2 which simultaneously solve this expression, this equation. In other words, what are we looking at? We have already seen this. What are we looking at? We are trying to look at x1 into 2 2 plus x2 into 1 1 is equal to 3 4. Now what does this actually mean? This means we are trying to look at scalars x1 and x2 such that the linear combination of the vectors 2 2 and 1 1 gives me the vector 3 4. So the question is, does there exist x1 and x2 real such that 3 4 is a linear combination of the vectors 2 2 and 1 1, right. Now, let us try to geometrically see what happens here and then try to get to the details of what we are going to do. So, let us try to draw this set of equations, but I am going to draw it in the vector way. I could actually draw it as equations, I mean straight lines where we have this x 1 and x 2, I have 1 2 3 4 5 6 1 2 3 4 and so on. So, I will take this, I will mark these points 0. Now, the two equations that we have are x 1 2 x 1 plus x 2 is equal to 3, and the other equation that we have is 2 x 1 plus x 2 is equal to 4. Now, if I take 2 x 1 plus x 2 is equal to 3, when I substitute x 1 is equal to 0, x 2 is equal to 3, and when I substitute x 2 is equal to 0, x 1 is equal to 1.5. So, this is the line that I have, right, that is the line, this is basically 1.5. Now, the second expression, the second equation that you take, we have 2 x 1 plus x 2 is equal to 4, when x 1 is equal to 0, x 2 is equal to 4, and when x 2 is equal to 0, x 2 is equal to 2, that means I am going to have a line which is like this. Now, what we see interestingly here is that the two lines are parallel lines and they do not intersect. We, from our prior knowledge of lines, we know that if two lines intersect, then the point of intersection becomes the solution to the system of linear equations. Now, what we see here is that the two lines do not intersect at all, they run parallel, which means they do not have solution at all. But the question says solve for x 1 comma x 2 with that condition where 2 x 1 plus x 2 is equal to 3 or 2 x 1 plus x 2 is equal to 4. Now, looking at it from the column perspective or looking at it from the vectors perspective, how is it going to be like, how is it going to be? So, let us look at that. I have my, let us say x 1 and the x 2 axis. So, I have 0 1 2 3 4 5 6 1 2 3 4 5. So, let me mark the coordinates. I have this. So, the first vector that we have is 2 comma 2, let us mark the 2 comma 2. 2 comma 2 is basically a vector which is here, and 1 comma 1 incidentally is also a vector in the same direction. Now, what are we looking for? The vector 3 comma 4, 3 comma 4 is basically a vector which is here. Three comma 4 is basically a vector here, and what do we see? We see that this vector 3 comma 4 is basically along a different direction, and what we see here is there is no way that I can get this vector 3 comma 4 as, okay, probably I could even change this so that it looks a bit better. So, instead of 3 comma 4, let me change this to 4 comma 3. So, let me change this, of course it does not really matter, but let me just put it this way. So, the equations that I am going to look at are 4 3, and let me change this also to 4 3 so that it looks better. So, the B vector now changes to 4 3, and this also is 4 3, right. So, now what are we going to have? 4 3 is basically a vector which is here, 4 and 3, that vector is here. Now, this is the vector that I have, B vector that I have. This vector is basically the 1 comma 1 vector, and this vector is basically the 2 comma 2 vector. Now, what we see here is this line passing through the origin and along this direction of 1 1 is basically a subspace, that is something which we all know. So, basically the subspace spanned by 2 comma 2 or 1 comma 1 is the vector which is the line passing through the origin and through the point 1 comma 1 and in the direction of 1 comma 1. So, that is going to be a subspace. Now, what we see here is this vector B is not in that subspace, it does not belong to that subspace at all. So, the vector B is equal to, so the vector B which is equal to 4 3 does not belong to the subspace spanned by the vector 1 comma 1. Right. This is exactly the problem that we faced, that we looked at in the last couple of lectures back, where we said, look, I have a vector x and I have a subspace W and I want to figure out what is the vector which best approximates this vector x in that subspace W. So, in this case the subspace is basically is the what do you call, is the set of, okay, the subspace is going to be here. So, let me write the subspace as so the W subspace is basically k times 1 1 where k is real. That is a line passing through the origin. Now, the question is, there is no way that I can get this 4 3 as an element in that subspace, which means I cannot now find out. So, this implies there exists no scalars x 1, there exists no x 1 and x 2. Such that 4 3 can be expressed as x 1 into 2 2 plus x 2 into 1 1, right. This cannot happen at all because that is not in the subspace. Now, what do we do? So, the thing is, if you look at it, it still says the solution, the question still says, look, solve for x 1 comma x 2. We have not deviated from this question at all, solve for x 1 comma x 2. The problem is no such x 1 x 2 exists, no such x 1 and x 2 exists, such that whatever we had, B is equal to x 1 into the first column of the matrix A 1 plus x 2 into the second column of the matrix A, which is A 2. Now, we cannot say, look, no solution exists and we close the matter there. It does not really make sense to say that, look, it does not exist, so the chapter is closed, we are not going to do anything more. Even in real life, when we see, look, where there is a problem, we say that, look, there in real life scenario we always say this, okay, look, there is no treatment that is there for this particular illness. Now, what do we tell the doctor? We say that, look, it is okay sir, give some medicine or something, just make him recover from that particular illness, that is it. When there is no treatment, we say that, look, there should be some, there will be some kind of a problem, but ensure that this problem that comes out of this issue not which is not being solved, that is minimum. So, in the same case, that is exactly what we are going to do here. We do not have an x 1 x 2, that means A x is equal to B does not have a solution, does not have a solution. So, what do we do? So, what do we do? Best thing, we already know what we need to do. What do? We say that find the best representative or find the representative that best approximates, find that representative of B vector, representative that best approximates the B vector in the column space of A. we already know the definition of the column space of A or the range of A, which is nothing but the set of all possible linear combinations of the columns, or the set of all the vectors which could be expressed as the linear combination of the columns of the matrix A, that is called the column space of A. Now what we want to do is we want to say, look, find the representative that best approximates B in the column space of A or the range of A. So the moment you say that you get the representative which best approximates in the column space of A, it boils down to the problem that we have already solved. That means what is that vector which best represents B in the subspace which is basically the column space of A, right. So we essentially we write, so find that representative, which that is exactly what we have done. Now how do we get this? So how do we get this best representative? This best representative. The answer is known. Project B onto the column space of A. Or the range of A. Right, project B onto the column space of A or onto the range, that is the range of A. Now the moment you find this projection, so this let this projection be called as B hat, let this best representative of B in the column space of A be denoted as B hat. Be denoted by B hat. Right, fantastic. The moment you find that representative, B hat is now going to be there in the column space of A. The moment it is there in the column space of A, I can find, I may not be able to find x1 x2, instead I can find an x hat, which is basically say x1 dash and x2 dash, such that I get A into x hat giving me B hat, but subject to the condition that the squared error between B and B hat be minimum, and that is exactly what we call as our least squared solution. So what we want to do is we want to figure out this. So what we do, let us look at this. So we okay, so let us look at this. So for any x we know that Ax lies in the column space of A. Right, it lies in the column space of A. So ideally what we want is, B minus Ax to be equal to the 0 vector, because if B lies in the column space of A, then it will have a representation which is Ax, therefore B minus Ax must be equal to the 0 vector, or equivalently what we say is since B minus Ax is the 0 vector, we say that the length of this vector must be equal to the scalar 0, right. Now in our case that we saw, there exists no x such that B minus Ax can actually give you the 0 vector, therefore what we do is we can try to minimize, we can try to make B minus Ax as small as possible, right. So, in our case at hand, whatever x we take, whatever x hat we take for the given b, b minus a x can, the magnitude of that, the length of that can never be equal to 0, because b is not in the column space of A, that is something we know, not in the column space or range of A, right, it is not there in the column space of A. So, what we can do is, the best we can do is the following, we say that, so in such a case we try to minimize or b minus a x or make it as small as possible. Make it as small as possible, that is something which we can do, right. So, what we do is we want to find out okay. So, what we are going to say is, we say that if we can find a unique vector x such that b minus a x is minimum, we call such an x as the best solution, or we will say the best optimal solution to A x equal to b in the squared sense, in the, or in the sense of least squares, in the squared sense. Right, and what we do is we denote, we let that x be, let the best optimal solution be denoted by x dagger, solution be x dagger. Now, what are we going to say? We are going to say that we are going to say, we are going to look at this, we are going to say that, okay, whatever x you put in b minus a x here, you will get the length of this difference vector to be something, but when you put x dagger, the length that you get is the smallest, the least that you will get, that is why x hat is called the best optimal solution in the squared sense, or the least squared solution, right. So, what we want to do is we want to look at this. So, what are we going to say? We are going to say that b minus a x is smallest, because we already saw the orthogonal projection will give the least squared error. So, b minus a x is basically the smallest when a x dagger is the orthogonal projection of b, is the orthogonal projection of b onto the column space of A. right. Ax dagger is basically the orthogonal projection of B onto the column space of A. Now, what does that mean? That simply means the following. That means, if you take this to be the column space of A, let me take this to be the column space of A, where all the vectors are of the form Ax, and this guy is going to be the B vector, this is my B vector. Now, what we are going to say is, look, you drop this fellow is going to be my B hat vector, which is basically given by Ax dagger. Is that clear? That is basically the Ax dagger. So, this is the vector which is basically my Ax dagger. So, this is all here column space of A means you have all these vectors to be of the form Ax, that is exactly what we have written. So, what we have? We have this to be the B vector, this is the column space of A, therefore, this vector is going to be B minus Ax dagger. Now, what do we see here? B minus Ax dagger is orthogonal to all the vectors in column space of A. Let me denote column space of A to be the set of vectors which is Ay, where y is basically an element of Rn. So, here I am going to say y is in Rn. So, what are we going to have? We are going to say that, look, so B minus Ax. So, we want B minus Ax dagger, that is the vector that you are going to get, which is basically the B hat vector, B minus Ax dagger to be orthogonal to every vector, to be orthogonal to every vector in the column space of A, in the column space of A, right. And every vector in the column space of A, you know how we denote it. So, every vector in the column space of A is going to be in the column space of A is of the form let us say Ay, where y is going to be an element of Rn. So, what do we have? We have the following, we have Ay dot B minus Ax dagger to be equal to the scalar 0, dot product is being 0. So, which is nothing but what are we going to have? We have this which is given by. So, what we have? We have Ay the transpose into B minus, this implies B minus Ax dagger, that is going to be equal to the scalar 0, which is nothing but y transpose into y transpose, let me write this as y transpose A transpose into B minus Ax dagger is equal to 0, which implies we have this y transpose into A transpose B minus A transpose Ax dagger is equal to 0, which is essentially saying y dot A transpose B minus A transpose Ax dagger to be equal to 0, right, for all y. For all y this is equal to 0. Now, if you want to look at that vector which is orthogonal to every possible vector y, there is only one vector which is orthogonal to every possible vector y, and that is the 0 vector. Therefore, this must be equal to the 0 vector, which implies A transpose B minus A transpose Ax dagger is equal to the 0 vector, which implies A transpose Ax dagger is equal to A transpose B, which implies A transpose A the whole inverse into A transpose A x dagger is equal to A transpose A the whole inverse A transpose B, which implies x dagger is equal to A transpose A the whole inverse A transpose B. Now, this is a fantastic result that we have. What does it say? It says, look, the best optimal solution is basically given by A transpose A the whole inverse A transpose into B. Now, what is interesting, let us see one more stuff here. We all know that whenever we have a matrix, say n by n matrix, and say invertible n by n, invertible, and we want to solve A x equal to B, we say that B is equal to A inverse, okay, x is equal to A inverse B. We say that x is equal to A inverse B. Now, let me call this as like equation star. So, what I do is I compare this equation star with this expression that I have. What is it? I have x dagger is equal to A transpose A the whole inverse A transpose into B. Now, if you look at these two expressions, the left hand side seems to have only x, but the right hand side here we have A inverse, and here there are terms which pre multiply this B, which is A transpose A the whole inverse into A transpose into B. So, what we are going to do is we are going to give a name for this matrix A transpose A the whole inverse A transpose, and that name is basically the pseudo inverse of A. Actually, if you look at this, so this is basically the pseudo inverse. So, what I am going to have is I have x dagger is equal to, I will say A dagger into B, where A dagger is equal to the pseudo inverse, which is A transpose A the whole inverse A transpose. Okay. Now, if you look at this, it may sound a bit complicated expression, it may look a bit complicated expression, because you have x is equal to A transpose A the whole inverse into A transpose B and stuff and all. But what is interesting is we can, after all, what we want to do is we wanted to find out the projection of the vector onto the column space of A. Suppose if I have a vector, let us just take two vectors, suppose I have a vector u and a vector v. Now, what we have is projection of v onto u, the projection of v vector onto u is given by v dot u divided by u dot u, right, the scalar. So, if I take this, this is basically projection of v in the direction of u. So, this is going to be this into, let us say you have your u cap vector or the unit vector there, right. Now, which is nothing but what we have is we have let us say u transpose v divided by u transpose u in the direction of this is what we have, right. Now, if you look at this expression, I can actually write this as u transpose u the whole inverse u transpose v. Oh, this is precisely, this looks very similar to what we have here. Whatever we have here, this it actually looks very similar to this. So, what we have u transpose u the whole inverse into u transpose into that vector v, that is exactly what we have had here. So, if I multiply this by A, I am going to get a projection matrix here. Suppose if I multiply this with that vector A. So, in this case if I make it A x dagger, I am going to get A, let me do this, A x dagger, we know what A x dagger is. A x dagger is nothing but orthogonal projection of B onto the column space of A. Orthogonal projection of B onto the column space of A, right. That is exactly what we are doing here also. So, what do we do? I have A x dagger, which is nothing but A into A transpose A the whole inverse A transpose B, and I want to look at projection of the vector v onto the direction of u. I want to look at the, this is the scalar that I get, and therefore, in the direction of u should be the u vector. So, what I get is I am going to have u transpose v divided by u transpose u in the direction of u, but this is going to be a scalar. So, what I will do is I will bring this vector here. So, I am going to get this as u into u transpose v, I will take this as u into u transpose u the whole inverse u transpose v, that is exactly what we see here. So, this idea of pseudo inverse is not something I mean which we have not paid attention to probably when we looked at in terms of vector, because that vector is also going to be a m by 1 vector m by 1 vector, right. So, we have not probably paid attention to it, but the expressions are the same here, except that here you have taken it as a vector, there we are going to take it as a collection of vectors, that means the matrix with certain number of columns. So, that is what we have here. Now, why did we even look at this? Why did we even look at this? So, this idea of pseudo inverse comes handy when we try to fit, we were looking for, when we try to fit whatever polynomial that you have for a set of data points. And this is exactly what we will see when we try to do the least square solutions, when we do the optimization part of it towards the end of this course, let us say week 10 most probably, we will see this optimization problem of fitting this least squares. Now, what we have done is the same thing, but there we will do it in terms of the matrix calculus and stuff. We will see that essentially you will get back the same expression, which is A transpose A the whole inverse A transpose B. So, what we will do is in the next class when we come back, we will take an example and see how this curve fitting actually happens. I will just take a couple of points and then I will take an example and then see like how does this curve fitting happen, especially with this kind of matrices, this kind of, when you have more data points, and let us say the best part is like say you want to in machine learning, the first thing that you would look for is like, can I fit a straight line, which means I am going to do some kind of linear regression there. So, what I will do is I will take some data points and then see if we can fit a straight line. I will specifically take an example where the points do not form do not fall in the same straight line. So, what we want to do is we want to find out that line which is going to be a best fit for the given data, and that is going to be an extension of this. We will see this example now, and probably when we go to week 10 where we are going to look at it in terms of calculus, matrix derivatives and stuff, optimization problem, we will see the same thing and we will get the same result there, right. So, what we will do is in the next class we will take an example for this particular pseudo inverse and least squares fit, and we will also look at, see in this case what we have done is we have assumed that A transpose A is invertible, that means the rank of A and the rank of A transpose and the rank of A transpose A and A transpose are all the same, and therefore we assumed that the matrix A is a full rank matrix. Only when it is a full rank matrix, that means if A is an m by n matrix, the rank is n, then A transpose A is it will be invertible. Now, what happens if we have a wide matrix where the rank of the matrix is equal to the number of rows and not the number of columns and so on? We will look at that in the next class after we see that example, and then what we will do is we will look at the idea of singular value decomposition and principal component analysis and support vector machine. So, in the next class when we come back we will take an example and work out this and follow it up with the pseudo inverse for a case where we have lesser amount of data with more number of parameters. So, we are going to look at that. Namaste.